So here, this is the outline of chapter 29. So first we will talk about magnetic field due to a current. So if I remember correctly, it's about the Biosava Law. Biosava Law. So tells you what is the B field generated by a small segment of current. Okay, and then we'll talk about forces between two parallel currents. So in the last part of the previous chapter, we talked about if there is a current, there is a current in the magnetic field, then there will be a force acting on it. So here it tells you if there are two parallel currents, what will it be? There will be forces between them, because as I mentioned here, we will have a current, it will generate magnetic field. So if we have parallel currents, then this current will generate B field at the other current. So there will be forces acting on the other current, and vice versa. The other current will also generate B field here, so that there will be force acting on me. So there will be force acting on them. Okay, then we will talk about the Ampere's law. Ampere's law is the third law in the it's the second law in the Maxwell equation we covered. Okay, and then we'll talk about the solenoid, toroid, and then current coil as a magnetic dipole. Okay, so this is just an overview of the Maxwell equation. So in chapter 23, we already know what is Gauss' law, although in this textbook or in the slides I show, we didn't use this notation, we didn't use D, but yeah, some other textbook use this kind of notation. Okay, so here we will also talk about the Ampere's law, and then in the next chapter we'll talk about the Faraday's law. Okay, so here it talks about the magnetic fields due to a current. So so here you can see a wire, and then we assume the current is going from bottom to top. Okay, so this wire is not straight. Okay, so in that case we can try to cut this wire into many segments, and every segment you can consider is a straight line. It's a straight line. So here the problem is, suppose we have a current going this way, and then we try to determine the B field generated at this point by this wire. But yeah, as I mentioned, this wire is not straight, so we try to cut it into many pieces. So for every small segment, we try to determine the dB generated at the same point P. And finally, we can find, let's say this one, this is dB1, and then for this one, this is dB2, and then dB3, so on and so forth. And then we find all the dB, 1, 2, 3, 4, 5, 6, so on and so forth, and on this point, and then we integrate them together to get the overall B generate this point. So here is what the so-called the Biosava Law, or law of Biosava mentioned. Okay, so it says the magnitude of the field dB produced at point P at distance r by current length element ds turns out to be this expression. Okay, so actually this is a law, so don't ask how we can derive it. No, we cannot derive it. So it's a law, it's just induced by some experimental result. Okay, so actually, so this is the Biosava law. So let's see what every variables about. So first one, we can see this is mu naught over 4 pi, mu naught over 4 pi. Actually, this, I will say this equation is quite similar to the Coulomb's force. Let me try to write it out. The Coulomb's force is like F equals 1 over 4 pi epsilon naught and then Q1, Q2 over R squared. Okay, so here we can see R squared, we can see 4 pi, we can see mu naught on the top, we can see epsilon on the bottom, and then we can see something, and then something, and then we still have sine of theta here. Of course, it should be something like a cross product. Okay, but of course this is a scalar product, so slightly different. Okay, maybe something like this. Yeah, so you can also see later for some equation in for the E field and some equation for the B field, they have a relationship called the duality, which means that if you try to change some variable from the E field version to the B field version, and then yeah, the equation will look like the same, which means that if you just change E field into B field and then something else, maybe like the electric dipole moment to magnetic dipole moment, just I mentioned in the previous chapter. For the torque, it is like P which is the electric dipole moment, and then cross the E field, and then for the magnetic version, it is like the torque equals mu, which is the magnetic dipole moment cross the B field. Okay, so here, and one thing interesting is that we should try to change epsilon naught to 1 over mu naught. Try to change it like this. Okay, so they have a reciprocal duality. Okay, so here you can see we have an epsilon naught on the bottom, and then so you should change it to 1 over mu naught, so it goes to the top. Okay, so what is mu naught? We still don't know what is mu naught. So here, mu naught is mu naught is a constant called the permeability constant. Okay, so epsilon naught is called the permittivity constant. 电导率 so this permeability constant is called 磁导率 磁导率 Okay, so whose value is defined to be exactly 4 pi times 10 to minus 7. 4 pi times 10 to minus 7. And similar to epsilon naught, it usually does not occurs independently. Usually it will occur like a 1 over 4 pi epsilon naught as a k. Here, for the mu naught, it also occurred like this one, mu naught over 4 pi. Okay, so for me, I will remember it like mu naught over 4 pi is 10 times minus 7. For the SI unit, I don't really remember. Yeah, I don't really remember. So, but at least I will remember the numerical value. Mu naught over 4 pi is like 10 to minus 7 with the SI unit. Okay, so here we have mu naught over 4 pi, so this is a constant, and then current, nothing special. And then ds is like, this is the segment. And then ds is the tangent line at this point, and also is follow the direction of the current. So this is ds. And then theta, okay, let me talk about r first. R is the distance from this segment to the point you concern. Okay, so this is the r, the distance between these two things. Okay, so as much as this is very small, so you can regard it as a point. So you can find the distance from here to here. And then theta is the tricky thing is that, okay, this is ds, and then this is r. So we have the angle between them, sine of theta. So you can simply imagine that it is something like a cross product. It's something like a cross product. And then here you can see we have an arrow here, which means that dB in this figure is pointing into the page. So how can we apply the right-hand rule is that, so you just follow the direction of IDS or DS, so this way, and then you cross it to the R vector. R vector is from the segment to the point you concern. This is R. So if you use right-hand rule IDS cross R, so your thumb is pointing into the page. So like this. Okay, so this is the scalar form, and here it writes out the vector form of the Biosava law. So here dB vector, so mu naught over 4 pi is the same thing, R squared is the same, I is also the same. So the final thing is that ds cross R hat, ds cross R hat. So you may feel like it is a bit strange, we don't have R here. So this R hat is the unit vector in R direction, so that it does not influence the magnitude here, because when you consider ds cross R hat, so it should be something like ds times the magnitude of this one, which is 1, and then sine of theta, which is the theta is the angle between these two vectors. So this thing is actually the same as this one, so there's no problem here. So yeah, this R hat is a bit tricky. Don't try to plug in or R is the distance here, then you make mistakes. For some of the textbook, it will write as ds and then cross R and then over R cube, so that it doesn't need to consider whether this is a head or an arrow. Yeah. Some textbook will write it in this style, but actually they are the same thing. So overall, this is actually the so-called the Biosava law, or law of Biosava. Okay, so here we talk about the long straight wire carrying a current. The Biosava law gives for the magnitude of the magnetic field of a perpendicular distance out from the wire B equals mu I over 2 pi R. Okay, so here the condition is long straight wire. Yes, straight means 直嘛. Okay, and then long, how long is it? It means infinitely long. Infinitely long. 无限长的. Okay, so here we assume there is a wire which is infinitely long going into the, actually the current is going into the page. So here you can see an arrow, and you can actually find the B field for the whole space. Every point you are able to know. Okay, so the magnitude is mu 0. Mu 0 is the constant we just mentioned, 4 pi times 10 to minus 7. And then this 2 pi is also a constant. R is the distance from this wire to the point you concern. Of course, it's a perpendicular distance, which means they should be on the same plane, and then you draw the line. So that line is perpendicular to the wire. And then I is the current, so nothing special. Okay, so here we also need to determine the direction of the B field. So again, we should apply right-hand rule to determine the direction of the B field. So here you can see there are many green circle, which is concentric. Okay, so yeah, the direction follows the right-hand rule. So you use a thumb pointing into the page in this figure, which means that your thumb follow the direction of the current, and then your forefinger will just follow the direction of the B view. So here you can see all the B view line are clockwise as the current is going into the page. Okay, so for every single point, so as you know the definition of the B view line, for every point, just say this one, the direction of the B view is the tangent to that line. It's the tangent to that line. So yeah, so you see a circle, so tangent line, so which means that this line and that line is perpendicular to each other. Okay, so later we will derive it. So don't but we first talk about likewise for the semi-infinite straight wire, which means that it starts from 0 and then go to infinity. So we just cut the other half. Okay, so likewise for the semi-infinite straight wire, the magnitude of the magnetic field at the perpendicular distance out from the wire is actually the half, because you only have a half of the wire. So you only have the half of the B field magnitude. Okay, so here we talk about how to derive this elegant equation. So yeah, so actually of course we need to apply the Biosava Law. The Biosava Law, dB equals mu naught over 4 pi times IDS times sine of theta over r squared. So this is the Biosava Law. Okay, which means that here we have the wire going to infinity far away, and then here is negative infinity far away, and then we try to cut this wire into many small segments. Okay, so this is the point P we concern. So let's consider this is the axis to be 0. So it goes this way to infinite far away, this way also go to infinite far away. Okay, so for every segment, just say this one. Just say this one. We call this one ds. And then of course this one will generate the B field at here. Okay, so here we can simply use the right-hand rule to determine the direction of the B field. So for example, for this one, ds pointing upward, and then r is pointing this side. So if you use right-hand rule from ds to r, then your thumb should be pointing into the page. And so you can simply verify it for the other point. Let's say for this one, ds always also pointing the upward, and then r pointing this side. So it doesn't influence the direction of dB. So for the whole wire, dB also pointing into the page for this point. Okay, so yeah, and then we can simply find that if we just find the symmetrical point, so for example this is plus s, and then we find something at negative s, which is something here, it should generate the B field. Yeah, this is the r, this is the direction of r, and these two segments should generate the same dB at point P, because we have this is theta and this is also theta. These two theta adds up to be 180 degrees, because if this is s, this is s, these two triangles are the same thing. These two triangles are the same thing, which means that this angle and this angle are the same. So this way, this angle, this one is not. Yeah, maybe I can just call it. This is theta. This is 180 degree minus theta, and you can, and I suppose you should know this trigonometry identity, which is like sine of 180 degree minus theta equals sine of theta. Okay, so which means that for this segment and this segment symmetrically, all the other variables are the same, and also sine of theta are also the same, which means that if we need to integrate from negative infinity to infinity for dB, so this is an even function, so then we can just cut it by half from 0 to infinity, and then we multiply by 2, so just do something like this. And this also explains why we have this one. So if we only have half of the y, it just generates half of the B field. Okay, so here we have this thing, and then we try to plug in this expression here. So these two will partly cancel with 4, so we only have 2 pi here. And then mu I is the constant, so we just put it out. And then, so we have a ds put in here, sine of theta put in here, r square put in here. Okay, so far, not so difficult yet. And then, okay, so here we would like to determine r. Actually, we need to integrate over ds over s. So r is, of course, a function of s, because this is capital R, which is a fixed value. This is capital R. This is capital R. So for this right angle triangle, s squared plus capital R squared is small r squared. So we take the square root on both sides. We have small r equals this square root of s squared plus capital R squared. Okay, and this is theta, which means that this is 180 degree minus theta. So sine of theta will be like capital R over small r. So sine of theta equals sine of pi minus theta equals capital R over r. So it's still some high school trigonometry. And then we just plug in r to be this expression here. So we have this one is a function of s, and then capital R is a constant, so we can do the integration now. Okay, so from here to here, so outside part will be the same, and then here sine of theta is this one, and then r squared will be this one square, which means we have a one order and then 1/2 order, so we altogether have 3/2 order, 3/2 order in the denominator, and then this is a constant. Okay, so yeah, so integrating this one will give you this expression. Yeah, so I think you need to use some trigonometry substitution, which is like S equals capital R tangent theta for this kind of a substitution. Then you plug it in, and then you do some cancellation. Finally, you can find out the antiderivative is like this. Okay, so yeah, so you can try to practice it at home if you have interest. Yeah. Okay, so yeah, so this is the antiderivative, and then you finally evaluate this antiderivative from 0 to infinity. So if we plug in s to be 0, it is nothing but 0. Yeah, it is nothing but 0. If we plug in infinity, it should be 1. It should be 1. So it is 1 minus 0, which is 1. So finally, B is this expression. Okay. So far, any questions? Okay, so we will use this expression frequently. Frequently. This is really useful later on. Okay, so next thing is here if we have, we don't have a straight wire, we we have a wire of a circular arc, Okay, so here it says the magnitude of the B field at the center of a circular arc of a radius r and center angle phi in radians carry current like this. Current like this. So here it is the arc, and then for the arc we can only find the B field at the center. For the other point, the expression are not so good looking. You need to use some computer software to find it, or just need to write a program to find it. Okay, so here it said if the central angle here, this phi is the central angle. If this is known, and also you know the current here, then the B field is something like this. Okay, so here we can just apply the Biosava Law. Biosava Law is something like this. And for this case, we try to cut this wire into many small segments. So for example, for this part, ds point to this side, and then R should of course from this segment to the center point. So which means that this is actually the radius direction or the reverse direction. So for the radius direction, it should be something pointing to that side. But here, of course, R is from this point to the center. Okay. And of course, this is a circular arc. So this ds and r are perpendicular to each other always. Okay, so here, to determine the B field at point C, so we apply the right-hand rule. So we have ds cross r. So ds pointing to the top right, and then cross to r head. So your thumb pointing out of the page. So we have the B field pointing out of the page. Okay, so for every segment, the DB always pointing out of the page, so they just adds up together. Okay, so in that case, here we have a B equals integration of dB from 0 to phi. So in that case, sine of theta is 1. Theta is always 90 degrees, as I mentioned. ds and r head are always perpendicular to each other. So we have a 1 here. And then we have mu 0 I, and then ds here, and then 4 pi r squared. Okay, so we integrate from 0 to phi. Actually, we should integrate the phi rather than ds, because the lower and upper bound is 0 and phi is the angle in radian. So we should do some change of variable. So it is like ds equals r times d phi prime. So I think it's still the high school mathematics, which means that for the segment here, the length of this segment is like the radius times the angle in radian, and the length will be r times theta. So as this case, if we have a ds here, it should be r times d phi prime. So we just change it to, so this is like mu 0 I over 4 pi r squared, and then integrate from 0 to phi, and then r times d phi prime. So this r and this r squared is partially cancelled, so we only have r here. And then finally, we integrating 1 d phi, so which is just phi minus 0, which is phi. So finally, we have this phi here. Okay, so we get this expression. And usually we will not use this one. We will usually use this one instead. This is a special case of the upper case. So for the center of a full circle, which means that here phi to be 2 pi. So if you plug in phi to be 2 pi and 4 pi will be partly cancelled. So we have a 2r in the denominator and then mu 0I on the top. So compare with the long straight wire, it is mu 0I over 2 pi r. Here we have mu 0I over 2r. We don't have a pi in the denominator. Okay. So here we have a sample problem. So it says the wire carries a current I and consists of a circular arc of radius r and central angle pi over 2 radian, and 2 straight sections whose extension is intersect the center C of the arc. What is the magnetic field B? Thus, the current produced at C. Okay, so it asks you the B field generated at point C. So here we have 3 segments. One segment pointing is this one. This is the second one. This is the third one. So we can quickly find that for segment 1. So suppose this is DS. So DS is pointing to the bottom right. And then R also point to bottom right because it comes from DS to point C. So R hat and DS point to the same direction, which means that the cross product should be 0. Which means that for segment 1, the B field generated at point C should be 0. And similarly, for segment 2, here DS point to the top right, and then R point to the bottom left. So they point to the opposite direction, which means that theta equals 180 degrees. So for the cross product, sine of 180 degrees is 0. So which means that B2 is also 0. So the remaining stuff is the third segment. The third segment is like B equals mu 0I phi over 4 pi r. We just make use of the previous the formula in the previous slide. And then here phi is so here we just plug in the values. Mu 0 over 4 pi is 10 times negative 7, and then times I is it does not provide what is I, so I just make it a variable here. And then for phi is pi over 2, so it is pi over 2, and then all over 4 pi already include here, so we don't duplicate it. So here we have r, so I still make it like r here, or maybe I just make it like mu 0 over 4 pi instead of writing 10 to negative 7 because other are still variable. So I just keep it like this. So here we can cancel pi and pi here, which means that the answer will be mu 0I over 8r. So this is the answer to this question. Okay, so I think it is quite easy. If you don't have any question, we can move on. So we have another sample problem. So it asks 2 long parallel wire carrying current I1 and I2 in the opposite direction. Okay, so here I1 is pointing out of the page, I2 is pointing into the page. Okay, so they are pointing to the opposite direction. Okay, what are the magnitude and direction of the net magnetic field at point P, assuming the following values, I1, I2, and D. So at point P. Okay, so it is like this is out, this is out, this is right angle. So which means that this one should be something like square root of 2 times r. Okay, so let's calculate one by one because we have two current. So it will generate B field. So I1 will generate B field at point P, and I2 will also generate B field at point P. And then, so this is B1, this is B2, then we'll add them together. Okay, so let's consider B1. B1 will be mu 0 I over 2 pi r. Because it is a long straight wire, we just simply use this equation. But here we have I1. Okay, so this is the B1. And similarly, B2 is mu 0 I2 over 2 pi r. Okay, so this is B1 and B2. Of course, we need to determine the direction of the B field by ourselves. Of course, I just give you. So let's see how we can know the direction of the B field. So yeah, here we can apply the right hand rule. For I1, your thumb pointing out of the page, and then your finger should be pointing in this direction. So at this point, the B1 should point to this direction because it should be something like a circle like this, and then this one should be perpendicular to the radius. So B1 point to the top left. And for I2, this is pointing into the page. So your thumb pointing into the page, so the B field should be something like this, in clockwise direction. Which means that the B2 at this point should point to this side. So this is clockwise. So this one is point to the top right, which is perpendicular to the radius. Okay, so actually we can be able to find the direction of B1 and B2. And as much as this one and this one are perpendicular, so B1 and B2 are also perpendicular to each other. So finally, the magnitude of B should be B1 squared plus B2 squared, and then take the square root due to the Pythagorean theorem. So we have a mu 0 over 2 pi r, and then we have a square root of I1 squared plus I2 squared. Yeah, because all the other stuff are the same, so we can regard it as a common factor. So you square it and then take the square root, so it remains the same. So this I1 and I2 are different in the two terms, so we have a square root of I1 squared plus I2 squared. Then we can just plug in the number. So mu 0 is 4 pi times 10 to the negative 7, and then over 2 pi r is, actually we don't know r yet, we only know d. So we can know that r is actually d over square root of 2. So which means that we can just plug in d. D is 0.053 over square root of 2. This is 2 pi r. And then we have a square root of I1 squared plus I2 squared, which is 15 squared plus 32 squared. So this number is 180 mu Tesla. 180 mu Tesla. Okay, so next we would like to find the direction. So actually, this is 45 degree. We can find this phi, and then we add with 45 degrees so that we can know the whole angle. So we don't really need to decompose it, this one in x and y axis, this one in x and y axis, add them together and then do something else. We just need to determine the angle of phi, then and then we add it with 45 degree, then it's okay. So here, for phi, B1, and then this is a rectangle. So this is B1, this is also B1. So for the phi, we know the tangent of phi, which means that tangent of phi is a b1 over b2, which means that phi should be arctangent of b1 over b2. And in that case, we have actually arctangent of b1 over b2. So this thing and this thing, if we divide them, we only left with I1 over I2. So which means it is actually arctangent of 15 over 32, which is 25.1 degree. So in that case, let us denote this as a theta. Theta will be 45 degree plus 25.1 degree, which is 60.1 degree. So yeah, so this is actually a 60.1 degree with the positive x-axis, something like that. Sorry, it should be 70.1 rather than 60.1. Yeah, it should be 70.1. Okay. Yeah. So far, any questions? No. Okay, so here we talk about the force between two parallel currents. Okay, so there are two cases. So the first case is like parallel wire carrying current in the same direction attract each other, and then parallel wires carrying current in opposite direction repel each other. So it's like same charge will repel each other, same polarity of charge will repel each other, and then opposite polarity of charge will attract each other. But here, same direction attract each other, and opposite direction repel each other. So let's see why it will be like that. Yeah, so let's see. Suppose these are two parallel wires, and then here we assume the current is from the bottom. So this one, we have the current from bottom left to top right for both. So they point to the same direction. Okay, so they have the same direction. Okay, so let's consider this IA will generate the B field at here. Okay, so how do we determine the direction of BA? So we use the right hand rule. Our thumb points to this direction, and then our finger will something like this. So you know that the B field is something like this. So at this point, it should be pointing to that direction. It is actually perpendicular to this wire, but it is a 3D shape, so you cannot see a perpendicular there. But I can tell you that BA is actually perpendicular to this wire. Okay. So here you can see this current IA will generate B field pointing downward at this point, and then we have IB pointing this side, which means that if you still remember what I talked in the last hour, so it is like FB equals I times L cross B. Okay, so L has the same direction as the current IB. So L is pointing to the bottom right, top left, top right, and then B is pointing downward, as I mentioned. So this Y generally be BA pointing downwards. So we apply right hand rule, L cross B, L point to that side, and then cross B. So FBA points to this side. And then you can practice it by yourself. You can verify that for the B field generated by IB here, Yeah, it will generate the B field. It will generate the B field. The B field is something in this direction. And then you can verify that FAB, okay, should point to that side. So FAB and FBA point to the opposite direction, which means that these two wires are attracting each other. You can also practice that if the current in these two wires are in opposite direction, they will repel each other, which means that if you just assume IB points to this side rather than top right, then you can verify that FBA and FAB points to still point to opposite direction. Maybe I just highlight in maybe use another color. For example, if I use IAB points to this side, then here FBA will point to this side, FAB will point to the other side. So they prepare each other. So you can try to practice it by yourself because I have already done this one and halfly this one. So actually you can practice it yourself to get familiar with the right hand rule, how to determine the direction of the B field, the magnetic force, something like that. Okay, so finally, we can also determine the magnitude of this FBA or FAB attracting or repelling the wire. So far we already have ILB, and also we know BA should be mu 0 IA over 2 pi R. But here we have D rather than R, so we write D here. Okay, so let's plug in this one into here. So we should have FBA should be, this I should be IB when we consider this one. So we have IBL BA. Okay, so we have IBL and then BA is mu 0 IA over 2 pi D. So in the denominator we have 2 pi D as this one, and then in the numerator we have mu 0 IA IB times L, or mu 0 L times IA IB. So from the Lorentz force, the second version of the Lorentz force, we can really get the expression of this force. So D is the wire separation and IAIB are the current in the wire. They do not need to be the same. So as we only consider the direction of them, whether they are pointing to the same direction. If they point in the same direction, the two wires attract each other. If they point to opposite direction, the wire will repel each other. Okay, so this is a quick summary. So they will tell it is parallel or anti-parallel. Anti-parallel means they are parallel, but the current points to the opposite direction, and then we call it anti-parallel. So they repel each other. So nothing special here. Okay, so let's stop here today.